Hi class, today we're going to talk about chapter 9.5. Today we're going to discuss the cross product. The cross product is a way for us to take two vectors and multiply them together and get a new vector out, right? So the dot product, we took two vectors and multiplied them and got out a number, a scalar value. Today we'll get out a new vector. And that new vector has some really cool properties in relation to the two original vectors that we use to multiply in order to get our cross product, our new product. So before we talk about the cross product, we have to talk about what's called the determinant. We're going to talk about the determinant a lot later on in chapter 10. So right now we're just going to introduce it, and we will reintroduce it and talk about it in depth in the next chapter. But for right now, we're just going to talk about what the determinant is. So if we have two vectors in R2, meaning they're two vectors that have two elements each, so V1, our vector V is V1 and V2, and our vector U is U1, U2, then we can put them into what's called a matrix. Okay, so our vector V will make up the first row in the matrix, and our vector U makes up our second row in the matrix. We always give a matrix a name. Generally, we call it A, and if we have a second matrix, we'll call it B, and if we have a third matrix, we'll call it C, and so forth and so forth. Okay. So again, the components of V make up the first row of A, and the components of U will make up the second row of A. Right. So here we have brackets around our matrix, and we're just putting in the elements of V and the elements of U in this manner to create the the matrix A. So V1, V2, that's my first row. So rows go lengthwise, right, from left to right. So this is row 1, this is row 2. Later on, we'll talk about matrices in depth, and we'll call this a column, right, column 1 and column 2. So one way to remember that is columns go up and down, right? A column will hold up a porch, right, or an overhang, right? An upwards beam is a column. When you go to a show, a baseball game, a football game, when you go into your bleachers, you go and you find your row. So rows go left to right. So that's an easier way to remember row. Column is the other direction, which is up and down. Okay. We call this a square 2x2 matrix because it has two rows and two columns, right? So it's a 2x2. It's square because the number of rows and the number of columns are the same. Okay. All right. So we can only find determinants of a matrix that's square. Okay. So in this section, we're going to stick to 2x2 matrices. We're actually going to extend that actually to a 3x3 matrices. But I need my matrix to be square in order to find the determinant. So the way I find the determinant is I have what's called the main diagonal. Right, so that starts in the first upper left position, and it moves diagonally along the diagonal. So that's V1 and U2. That's the main diagonal. The secondary diagonal is the same diagonal but moves in the opposite direction. So it starts in the lower left, and then I use the upper right term. Okay, so the determinant of A, notice here that the brackets are different. When I have a matrix, I use a square bracket, not a circle bracket. Right, not a parentheses bracket, a square bracket for a matrix. When I'm trying to find a determinant, that bracket changes to a straight line, very similar to like an absolute value. Okay, so square bracket means matrix, straight line bracket means determinant. This is an actual operation. DET of A is short for determinant of A. Okay, so I take my main diagonal, V1 times U2, and I will subtract from that the secondary diagonal, U1 times V2. So it's actually very easy to find this thing. You just have one multiplication and then another multiplication, and you subtract the two values. Okay. So here, this is just saying, notice the difference in the bracket notation. Again, straight line versus a square in terms of brackets represent different things. Okay. If we want to represent the determinant of a, or if we want to find a 3x3 matrix, right? So 3 rows and 3 columns, we break it down into alternating sums of 2 by 2 determinants, right? So that means we'll have a plus, minus, plus, minus, plus, minus, plus, minus. And what we're doing is we're finding sub-determinants of that 3 by 3 matrix, right? So that might sound a little confusing, so we're going to do an example. Okay. And so notice that this determinant for a 3 by 3, right? So we have a vector A, vector B, vector C. They all have 3 elements, so it's 3 rows, 3 columns. I'm finding the determinant. It alternates in sign. This is positive, minus, plus. Okay. Notice that the values in front that I'm multiplying this determinant by are the row elements on top, right? A1, A1, A2, A2, A3, A3. These determinants, you might say, how the hell am I going to remember exactly that this is B2, B3, C2, C3, then this one changes, then this one changes? There's actually a very easy way to remember this. If I take this A1 term, which I'm using to multiply, real quick, let's backtrack just a second. Let's notice that when I take the determinant, right, I'm taking this number and multiplying it. I'm taking this number and multiplying it, and I'm subtracting those two products. When I multiply two numbers, I get a number, right? 2 times 3 is 6. 4 times 5 is 20, right? I'm getting a number, and I'm subtracting two numbers, so my determinant is a number. It is not a vector, okay? Whenever I find the determinant of a matrix, I get a number out. So, this is A1 times a number minus A2 times a number plus A3 times a number. The determinant will give me a numerical value. So, again, A1, A2, A3, A1, A2, A3. So I'm doing this number times something, this number times something, but the opposite value. This number times something. If I look at my matrix and I take this number that's in the first row, first column, and then I delete the row and column that it's in. So I delete this row and I delete this column. Notice what's left. This thing, right? B2, C2, B3, C3. That's what's left. So I take A1, I put it here, I erase its row, I erase its column, and the sub-matrix that's left, I find the determinant of that. Okay, I go to my next value, A2, I change its value, right? So I subtract A2, and when I multiply it, I delete its row, I delete its column, and look what's left. This B1, C1, and this B3, C3. When I delete the row, delete the column, right? Delete row, delete column, this is left, this is left. For A3, same thing. If I delete the row, delete the column, this is what's left. 1 and 2 for B and C. Okay, so that's the easy way to remember it. Whatever value I'm on, I delete the row, delete the column, find the determinant of the submatrix. Okay, so again here, this is just repeating that. Notice that if we ignore the row and column for each A sub I, right, going along the first row, then the values that we get are 2 by 2 submatrix for which we take the determinant of. Okay, that is actually the definition of our cross product. So let's put this into a more formulaic method so that if you want to, it's important to know how this is made, but I'll also just give you the straight across formula, which is helpful, but it's a long formula, so it's a little bit easier just to know how to do it, right? So again, earlier we talked about the dot product, v dot u, which gives us out a scalar, right? The cross product is a multiplication that gives us out a new vector. So v dot u is the dot product. V with this is not normally an x, but you know, the multiplication times symbol is the cross product. Okay, so if we want to compute the cross product for two vectors, so when we do the cross product, we do this in 3 dimensions. We take two vectors in 3 dimensions, right? So 2 vectors that have 3 elements each, and what we do is we place an I, a j, and a k in just that form, so we don't expand this to the 1, 0, 0, and 0, 1, 0, and 0, 0, 1. We keep it as I, j, and k. And what we do is for A1, A2, A3, we use I, j, and k respectively. So A1 we just replace with I. A2 I replace with j. And A3 I replace with k. And then I put my two vectors that I'm trying to multiply, my v and my u. So v goes here in this row and u goes here in this row, and then I follow this formula. Okay, so my v cross product u is the determinant of I, j, and k on top, and then my v vector, and then my u vector. So v is first, so v is the first vector whose components I actually put down. U is second, so it's the last one that I put down. And then it's I, j's, and k's, right? X, y, and z in that case. Okay. So if we follow this formula for our cross product, that's how we get a new vector out. Okay. Because what's going to happen is, instead of A1, I'm going to have I here. So this determinant will give me a value for my x direction. This determinant will give you a value for our y direction, right? Because it's now I, j, and k. And k will be here instead of A3. So I will get a value times k. So that'll give me a new vector, right? Whose elements are in the direction of x, y, and z, because I'll have I, j, and k there. So it's breaking it down into its standard unit vector representation. So to do this formula, okay, we're just going to actually find this cross product on the general form so that we can find a formula, right? So I use I, and I cross out the row that's in, and I cross out the column that's in, and I use the remaining submatrix to find the determinant. So the vector I times the determinant of v2, v3, u2, u3, right? So that's the process. So what does that look like? v2, u3 minus u2, v3. Okay. Next we'll go to j, and we do the same thing. I use j, but instead of using the positive form, I'm going to use the negative. I cross out its row, I cross out its column, and the entries that are left, I will use for a submatrix, right? So remember, plus minus plus. So this is negative j, v1 and u1, v3 and u3. I find its determinant. So v1 times u3 minus u1 times v3 times negative j. Okay, so this is now a number times j, a number times I. Okay, and lastly, I do the same thing for k, and then I put them all together. So I'm using the entry k, delete its row, delete its column. I use the remaining submatrix and find its determinant. v1, u1, v1, u1, v2, u2, v2, u2, right? So that'll be k times v1, u2 minus u1, v2. Okay. Put these all together. This is my x, my y, and my z, right? Because the I vector represents x, the j vector represents your y's direction, and k represents your z direction. So the cross product between v and u is the determinant of this form every single time. Okay. Formulaically, it's I times the determinant of this submatrix minus j times the determinant of this submatrix plus k times the determinant of this submatrix, or as I times this value minus j times this value plus k times this value. And if I wanted to, I could put it into its vector form without the I, j's, and k's as the x component, y component, and z component. So we can follow the formula, but again, it's going to be beneficial to remember what the method defining this is. Okay, and so this is the formula that we can use if we want to try to memorize it. But again, there's going to be times where we're just going to have to really do this from scratch. So now to talk about the cross product. Okay, the vector that we get out here, it is orthogonal to both of the vectors that we started with. Okay, so if you think about it, if v and u lie in the same plane, like let's say that they were both in the x and y axis, for instance, or x and y coordinate system, if we found the cross product, it's going to point out of the paper towards us into the third dimension. Okay, now it's a little bit different than that because v and u they're in R3, so they have 3 elements each. So finding their cross product is going to give you another vector, but it's going to be orthogonal to both u and v itself. Okay, so the cross product v cross u is orthogonal to v, and the cross product of v and u is orthogonal to u as well. Okay, so this new vector forms a right angle with v, and it forms a right angle with u. So the dot product of this with v is 0, and the dot product of this with u is also 0. So that new vector we created, just to reiterate, this new vector, if I dot product with v is 0. If I take this new vector and dot product with u, it is also 0. Okay. All right. This follows what is called the right-hand rule. So when we get into physics, we get into bigger topics, even in Calculus 3, which is called torque. So the cross product is related to torque. We're not going to get into it right now, but what is important is what is called the right-hand rule. So I'm going to, obviously, I write everything out, but let's take a moment to just verbally explain this. Okay, so if you take your right hand, make a fist, and put it in front of your chest. Okay, so if you pull out your pointer finger should point away from you. Okay, if you extend your middle finger should extend to the left, right? It should point to your left. So your index finger points straight, your middle finger should be pointing to the left. These are your two vectors. One is v, one is u. They are in the same plane. They kind of like, you could put your hand on a table and both your pointer finger and your middle finger should kind of lay on the table. Okay. If you point your thumb up, that is the cross product. Okay. So your thumb is the cross product. So if you think about it, your thumb forms a right angle with your pointer finger, and your thumb forms a right angle with your index, with your middle finger. Okay. There is a gap between your pointer finger and your middle finger. You can move your two fingers, around in that same sort of direction, and you can change the angle between them. So the angle that we think of is the angle between your middle finger and your pointer finger, and then your thumb is your cross product. Okay, so let's kind of reiterate that in words. So if the right hand rule says that if we take our right hand, we make a fist, point our index finger away, our index finger is the v vector. If we extend our middle finger to point towards our left, that's our u vector. Okay, the space between our index and our middle finger is the angle theta that's created between our two vectors. And then if we extend our thumb upwards, then this is the cross product. Okay, and that cross product forms a right angle with our index finger and our middle finger. Now, I'll just talk about torque really quickly. If you notice your bottom two fingers, right, your pinky and your ring finger on your right hand, they kind of curl in a certain direction. Okay, that's what we call the direction of torque. So when you get into Calc 3, they will talk about torque, or if you take a physics class and they talk about torque, the right-hand rule is super, super important because you use your two vectors to represent your force and your direction. And then you find your cross product, and the curl of your fingers represents the torque. So like, for instance, if you are working on a car and you have a wrench and you are pushing down, that torque is represented by this right-hand rule. So we won't get into it here. It's kind of advanced, but we do cover that in the Calculus 3 course. Okay, so I have my vectors v and u, right? Index finger, middle finger. There's an angle between them. My cross product points up, and it is perpendicular to both of these vectors, to the vector v and the vector u. Okay, so that's the right-hand rule. It helps us to kind of orientate ourselves. So, if u is parallel to v, okay, then the cross product is 0. So if you think about it, if those two vectors point in the same direction, there is no angle between them, so there is no cross product. Okay. the length of the cross product. So again, remember the cross product is a vector, and the length of that vector can be symbolized with the length of v times the length of u times the sine of the angle between them. So notice this is very similar to our definition for the dot product. The dot product is the exact same definition, but it's the cosine of the angle between them, right? So they're very, very similarly related. Okay, this represents the area of a parallelogram that's formed by the vectors v and u. So remember what a parallelogram is. Parallelogram is like a rectangle, a square, a rhombus. It's basically anything whose opposite side are parallel to each other, right? So generally we think of a parallelogram as like a slanted rectangle. So our vectors u and v, when I place them tail to tail, that forms the skeleton of a parallelogram, which we know because when we add vectors, one of the methods is the parallelogram rule, right? We place those two vectors tail to tail, and then that main diagonal becomes the addition of the two vectors. So it's the same setup, but the cross product is the area of that parallelogram that's formed. Okay, so here I have u and v tail to tail. It traces out a parallelogram. There's an angle between u and v. Okay, so that traces out that parallelogram between us. This is the angle between u and v. Notice what sine is. Okay, so just how we had for the dot product we thought about this as the length of v. This was the length of u cosine theta, right? So here we're thinking about it as the length of v times the the vertical portion of u. So the length of v is the length of the base. The length of u sine theta is the vertical component here. That's the height. Okay, so for any rectangle, it's base times height. Okay, so if I dropped a perpendicular here, its length is the length of u, because remember for a unit circle, it would just be sine of theta. So we think of this as a circle with radius of length of u. So we have to extend the value of the sine as well, right? Multiply it by the length of u, that radius. And so this component is length of u times sine of theta. So the height times the base is an area. Okay, so base times height. This brings us to what's called the scalar triple product. This is basically when you have three vectors. One of them is a cross product, and you take that and you take the dot product with another vector. Okay, so it's the dot product of a vector with the cross product of two others. So it's really a mixture of the dot product and the cross product. So three vectors, two of them used to find the cross product, which makes a new vector, and that new vector, the cross product, you take the dot product with a third vector. So there's a cross product there and a dot product there. Okay, so find a cross product. This result is perpendicular to u and v, or sorry, u and w, and there's a third vector v that we use to take the dot product with it. Okay, so a way to expand this to a simpler version is to find the length of the cross product, and then it's the length of v times cosine of the angle between v and the cross product uw. Okay, so if the scalar triple product is 0, because remember, it's a vector dot product with another vector, so you're going to get out a number. If that value is 0, then v, u, and w are coplanar. So what does that mean? Well, we know u and w lie in the same plane. Okay, but if the dot product of this result with this result is 0, then v, u, and w all lie in the same plane. That means that there is no outward direction, right? They all lie in the xy plane, for instance, and there is no z direction. Okay, now that's a simplification because when we're in 3 dimensions, a plane does not have to be just xy plane or a fixed x value or a fixed y value. We can have planes that are slanted. So if you take a piece of paper in 3 dimensions, right? So you have a piece of paper in your hand, that's a plane. So however you can orientate that, it doesn't always have to be parallel with the floor. It doesn't always have to be right side up. It can be tilted. You can move in all kinds of different directions. So our definition of a plane, which we'll talk about later, has all kinds of different representations. So there's not always just like a flat sheet that's parallel with the floor, right? So if I have a vector u and v, maybe there is a plane that they both lie in. If the scalar triple product is 0, then that third vector is basically a linear combination of the other two vectors. Okay, I can make v out of those vectors u and w most likely. Okay, so they lie in the same plane. Okay, so the scalar triple product vu and w is equal to v1, v2, v3 dot product with the formula we have for this cross product, okay, which we had here. And if we start to move backwards, so let's actually like multiply this through, right? Or not multiply this through, but we'll start to bring this out. So we know that this definition is a determinant of a 2 by 2. This is a determinant, and this is a determinant, right? Because that's how we form this. So I have the determinant here, negative determinant here, the determinant here, because this was I, j, and k, and j was negative in direction. So if I do the dot product, I get v1 times this determinant, v2 times this determinant, v3 times this determinant, and I add them all together, right? So plus minus plus, because it's plus, minus, and plus. So notice that that's the same definition that we had for our ijk. So if I want to find the scalar triple product, I really just have to find the determinant where I have v first, whatever it is that I'm dot producting is the first one. Then for my cross product, u cross product w, u is in the middle, w is last. Okay, so if I want to find my scalar triple product, I just set up this 3 by 3, and then I find its determinant in the method that we've gone through in this class. Okay, so again, instead of having to find a cross product and then trying to find the dot product, I could just set this up and just find one cross product. Okay, it makes it a little bit simpler. The absolute value of the scalar triple product is the volume of a parallel pipette. So a parallel pipette is basically a parallelogram as a prism, right? So we extend it into 3 dimensions, and the absolute value of the scalar triple product is that value. So remember, this is a dot product of a vector and another vector. Dot products can be negative. So that's why we need to take the absolute value, because volume is always positive, right? Again here, volume is always positive. So again, recall that the dot product is length of v, length of a, cosine of theta, okay? And that the cross product is itself a vector. So if I let a be this u cross product w, then this formula, which is v dot product a, is really v dot product u cross product w, which is going to be the length of v, and instead of the length of a, it'll be the length of the cross product, okay, and cosine theta. Okay, so that's a geometric form for finding the scalar triple product. So I can find the scalar triple product by setting up this 3 by 3 matrix and finding the determinant, or I can find the scalar triple product by this geometric representation, which is using the angle between them, the length of v and the length of the cross product. Okay, so depending on what we're given, it's going to really determine which form we want to use. Like if I'm already given u cross product w, maybe, and the length of v, but I'm not given v, and I'm given the angle between them, it would be really hard to use this formula. But I would have everything necessary to use this formula, right? So depending on what we're given is what we want to use. So again, here I have u and w lie in the same plane. Okay. Then I have a third vector v. This is the cross product. So notice it forms right angle with u and it forms a right angle with the w. U is the base. Okay. W is another base. So if I multiply the length of w and the length of u together, that gives me the area of the base. And then I need to find the area of the height, but I don't need the length of u cross product w because that might be too large, but I can use the not the vertical component, but this is actually the horizontal component of v. Okay, so I can use this v, which would be cosine theta times the length of v. Okay, so u cross product w lengthwise gives me the area. We've seen that before. And v times the cosine of theta is this, which gives me the height.